Hello everybody and welcome back. We're looking at question number 2 now on the Galois paper from 2004. So it's a three-parter and let's see, in the diagram, which I don't know about the copy that you guys downloaded, but the diagram I've got not very clear. It looks like we've got an A, a B, and a C up there. So let's read and maybe the explanation will clarify our pictures here. In the diagram, the semicircle has diameter AB equal to 8. Okay, you can sort of make that out. Point C is on the semicircle, so the triangle ABC is isosceles and right angled. Okay? It's true that any point we picked would make a right angle, but having the isosceles one and the isosceles condition that AC is equal to BC, that's quite unique. Okay. Determine the area of triangle ABC. So that's the first thing we have to do. Well, I think the best thing probably to do would be to figure out the legs of these triangles. Yeah, I'm going to read through the whole thing. The two regions inside the semicircle but outside the triangle are shaded. Determine the total area of the two shaded regions. I think that would bounce off nicely from part A, because we could probably work out the area of the semicircle, subtract the area of the triangle, we're all set. In the C part, the semicircles are drawn on AC and AB as shown. There's a little gap over there, but show that the area of the semicircle drawn on AB is equal to the area of the semicircle drawn on AC plus the area of the semicircle drawn on CB. I don't really think that has a lot to do with the two parts up above, but I probably would want to know the length AC here, just because it would be a diameter, and from there I could get the radius. So definitely I think the way to do part A is figure out what AC and AB are, and then those become my base and my height, and get the area that way. So it's a good idea to read the whole question and plan things out, especially on things like the Galois, Hypatia, Fermat, or not Fermat, Fryer, because these questions, question 1 is designed to work all together, and question 2 is, it's all the same sort of concept. Okay, so I'm going to redraw my picture. We've got A, we've got B, we've got C up here. It's a right angle. I know these are the same length, and this is 8. Okay. So I'm going to let AC equal AB, or not AB, BC. Equal X. Since triangle ACB is right angled, usually you put the right angle one in the middle, I think is convention. Then by Pythagoras, or by Pythagoras' theorem if you want to say it that way, but usually by Pythagoras is all you need to do, because that's really the most common thing he's known for. We know that x squared plus x squared is equal to 8 squared. Okay, so we're going to have to go on to the next page, but we can simplify this. 2x squared is equal to 8 squared. 8 squared is 64. So x squared is going to be, divide both sides by 2, we get 32. So x is going to be the square root of 32. I wouldn't leave it like that, because there's a 16 in there. And the square root of 16 is 4. So I'd say something like 4 root 2. Root 32 is fine. I like getting as small a number under the square root sign as possible. So I like bringing out as many integer factors as I can. Okay. So this isn't what we need, but we do need to note that since it's right angled, I might say A, B, C, X, and X. So AC is a base, BC a height. So the area of ABC is 1/2 base times height. So 1/2 x squared. Well, we already worked out what x squared is. I didn't even need to work out what x is. I was just sort of going on autopilot. 32 over 2, we'll get 16. So 16 is our answer for the area of ABC. I'll put a little box around it so they know that that's an important calculation that I've made. Likely my final answer, although, not necessarily. But boxes are good for indicating important things to draw the marker's attention. And these things are hand marked, unlike, say, the Kaylee, another grade 10 contest, it's all done on sort of a Scantron. You bubble in things, it's fed through a machine. The results are back within like a week. But these things have to be marked. Okay? So it's always a good idea to remember that and make things clear, write neatly, don't write too lightly or too darkly, because humans have to read and interpret what you're doing. Okay, so B part, they wanted the area of these shaded regions. So I've seen many of these questions in the past. A great way to set these up is to find a way to write the shaded region as a sum of smaller regions that you can figure out, like smaller rectangles and triangles and things, or a difference between bigger shapes like circles minus triangles, circles minus squares, and rectangles, and achieve them that way. So I notice the shaded region are the difference in area of the semicircle and triangle ABC. And I'll just remind them which by part A I know has area 16. That way I don't need to recalculate that out. I'll just say, I know this, it was in part A, go check if you don't believe me. This is the number I'm working with. So I'll write down my plan of attack. So let's work out the area of the semicircle. And subtract. Okay. So, area of the semicircle. Well, redraw our picture once again. We don't really need C up there. We just sort of need AB. AB is a diameter. So 1/2 of this 8 value, 4, is the radius. Formula for the area of a semicircle is 1/2 the area of a circle, because it's a semicircle. Circles are pi r squared, so we're going to have 1/2 of pi r squared. So this will be 1/2 pi, and our radius is 4 squared. So we'll have 16 over 2 pi, or 8 pi. The area of the semicircle, not the area of the semicircle, the area of the shaded regions, is 8 pi minus 16. And I might stop for a moment and ask myself, does this value make sense, 8 pi minus 16? Because, 8 is less than 16. If pi isn't big enough, maybe we've got a negative number here. So I stop and I think, 8 pi, well, pi is bigger than 3. So 8 pi has got to be bigger than 8 times 3, that's 24, and that's much bigger than 16. So I am sort of in the clear. I may have some wrong numbers, but at least I've sort of done a sanity check. Does this number at least make sense as an area? Okay. So, what else have we got? We've got C part left to do. And C part requires an actual proof. A lot of these things have just sort of been numerical calculations. A and B part, 16, and then 8 pi minus 16 didn't really need work shown. But C part, we are actually asked to explain why this result happens. Okay. Okay, so semicircles. So, actually, I think this is probably true of any right angle triangle you draw in here, not just these isosceles ones. Geez, one thing we could do is we could show that, well, we know the area of the big semicircle, AB, and we know these ACs and BC lengths, they're x, which is 4 root 2. We could get their radii and add them together and show that it really is. I think that's probably the best way to do it. So I would say something like, from B, the area of our AB semicircle is 8 pi. So let us compute the area of, so we need AC and semicircle CB. So both semicircles have a diameter of x equals 4 root 2. So they have radius 1/2 x, which is going to be 2 root 2. Using our formula, for the area of a semicircle, they each have area 1/2 pi times the radius squared. 2 root 2 squared is 8. 8 divided by 2 is 4, so they'll both have area 4 pi. So what do we want? We wanted to say the area AB, which is 8 pi, can be broken down into 2 copies of 4 pi. AC plus CB. And there I've shown it. Now you might be worried, well, you haven't written out in complete sentences, you've just drawn little semicircles AB. If you're worried about that, of course, write out semicircle. I mean, some of what I do is just a little bit of abbreviation, but if I were marking, I would say, yeah, I can clearly follow what he's doing, and yeah, he's done what he needs to. I just didn't want to write every single time, the semicircle whose diameter is AB, the semicircle whose diameter is AC. I mean, if we go back to the actual question they asked us, they couldn't even fit that on one line. Okay, it's clearly a bit of a mouthful, so, you know, why not abbreviate it in a nice, meaningful way? Okay, I had little pictures representing whichever semicircle I was talking about. So I would say that's clear. You might disagree, in which case, write more. That's fine. So that does it for question 2. What I wanted to do, actually, for a moment, and this is just an aside, I think the result is true no matter where I place my other point. So C on the semicircle must make triangle ACB right angle. This is a nice result. If you didn't know it, you can commit it to memory. If you have a diameter semicircle and you take any point connected up to the end points of your diameter, you will get a right angle triangle. So I'm going to call this guy C, A, B. So then a squared plus b squared is equal to c squared. By the way, I once again would like to remind you this has nothing to do, this is sort of a more general way to prove c. We've already finished c, this is just a little extra stuff. So then we've got this result by Pythagoras. If I were to draw semicircles, and I admit these are really terrible looking semicircles here. So the semicircles have radii. Okay, the big one has radius c by 2, because c is its diameter. Then we've got b by 2 and a by 2. So now, if I have the radii of these semicircles, their areas, the area of this one is 1/2 pi my radius squared. And that's going to be 1/2 pi. The 2 squared on the bottom becomes a 4, and we get a c squared on top, so this will be 1/8 pi c squared. But c squared can be written as a squared plus b squared. Okay. Oops, we forgot a pi. So this will be 1/8 pi b squared plus 1/8 pi a squared. But then that's 1/2 pi b/2 squared plus 1/2 pi a/2 squared. But that's exactly the area of the semicircle that's got b, and the tinier semicircle that's got, not area b, diameter b, and the area of the semicircle that's got diameter of a. So this result is true regardless of whether or not c is that nice special point where you get an isosceles triangle. This is true in general. I think this is a nifty proof. Might go over some of your heads because I'm going through it a little quick. But I would say for the most part, if you stare at it, it kind of follows logically. What did we need for it? We needed Pythagoras' theorem, and we needed to know that a point on a semicircle always gives us a right angle triangle. Now, the question, they told us that. They gave us that for free just in case you didn't know that. If you didn't know it, now you do. That's something you can take and learn and apply in other geometry situations. But I would say the result here is nice to follow. It's more general than what they were asking for, and that's always kind of cute when you can give them more than they ask for. This would be a perfectly fine solution. The one we did before would also get you full marks. This is sort of showing off. But it's also something to keep in mind because maybe on the Hypatia, where they ask slightly harder questions, they might not tell you that you've got that isosceles triangle stuff. You might not be able to compute the diameters or radiuses, and you might be asked just prove this nice big general result. So this is a great sort of thing to know. Okay, but that does it. I got nothing else I want to say for part 2, or not part 2, question 2. We're going to move on to question number 3 for the Galois in the next video. So thanks for watching. I'll see you then.